much for accepting the paper into this conference. I'm going to be talking about improving the capabilities of large language model-based marketing analytics copilots with a combination of semantic search and fine-tuning. And really, this generalizes pretty much to any analytics use case, and many of the tests that we did were not actually specifically on marketing data. My name is Jim Snyder. I'm a staff machine learning engineer at Adobe. And prior to that, I actually, of all things, did my PhD in computational chemistry at Stanford. So this has been quite the change. So I'll give you a little bit of background about LLMs and large language models before I get into kind of the results. But first, let me introduce the team members. So I especially want to thank Yilin Gao, who is an intern at Adobe during this time and was responsible for a lot of the core work. She'll be joining Adobe pretty soon, but it was a PhD candidate at University of Southern California, and then Sai, Yancheng, and myself as well. So the first thing I want to cover is basically what LLMs are. And LLMs are essentially a large transformer neural network that predicts new text from prior text. Technically, they don't have to be transformers, but pretty much all of the major ones are. And to the right, you have a diagram of a transformer architecture, which kind of shows like blocks at a high level what they are. And the transformer architecture is actually pretty simple structure. It's very similar to the traditional feed-forward neural networks that people have been using for quite some time, but there are a couple of very significant and important innovations. So, and I'll kind of highlight them over here. The first of which is the embedding process. And this isn't as much of an innovation for text embedding, which has been done for quite some time, but the base structure of this neural network was not originally designed for sequence data. And so they needed to sort of add capabilities to understand information about the sequence. And so one of those was adding positional encoding, which encodes the sequence of each word in the text sequence using a series of sines and cosines usually, but there are other ways that can be done. The other thing is in this orange block right here, which is called masked multi-headed attention. And basically, these are a series of tensor products essentially that allow the LLM to focus on different parts of the input sequence. And this is the mathematical formula right here, where Q, K, and V are called the query, key, and value matrices. They're responsible for attending to different aspects of the input. Now, actually, if you just use this, the performance of transformers isn't really any better than recurrent neural networks. And so the other key innovation was actually to use multi-headed attention, which basically involves a bunch of these operating on different replicas of the input that allow it to learn more complex functions. And then finally, masking is a pretty important part of this because as it stands right now, the entire input is fed at once. And in order to make a prediction about some sequence event in the future, you can't use future information. And so masking is done and essentially just involves zeroing out words that occur after the current word. The original transformer architecture is proposed by Vaswani et al. Back in 2017, but this architecture diagram will differ a little bit from that beyond the fact that it also doesn't have an encoder component of it and isn't used for machine translation. This is actually the architecture for GPT-2 from the 2018 paper. And the more recent GPT models probably have a similar structure, but they have a much larger number of these loops. But we don't know for sure since they aren't made public. LLMs could be useful for a variety of different reasons in marketing analytics. As someone that works as a kind of practitioner in this field, it's often the case that there are enough questions that we have to answer from potential customers that we realistically can't get through all of them. And so we kind of end up prioritizing the most important ones. And so the purpose of having one of these copilots would be to reduce the amount of human effort required to answer customer questions and by extension, actually answer more of their questions in a more efficient manner. is also provides more flexibility in terms of insights beyond static dashboards. And typically, marketing analytics software involves producing a dashboard that works for the highest number of different customers or the average customer, so that you don't have to do tons and tons of customization, which would significantly drive up the cost of an implementation. And then, beyond this, a lot of people may want to read documentation. This can take a long time, but this can make information lookup much more efficient for customers, and can, as part of the first bullet point, can help resolve challenges more quickly. I do want to briefly comment on this photo right here. So this photo is actually produced by Adobe's text-to-image generator, Firefly, with a prompt below. And I included a few of these here just for fun, really. And you can see, that this actually does, I think, a pretty good job capturing what I input. And so I was pretty happy with this result for this presentation. So despite the fact that LLMs could be useful, they do have some significant problems in terms of deploying them. One of the bigger ones is context length limitations. And so context is the number of words or actually tokens that can go into the model as an input. And for the largest OpenAI models, last I checked, it was 32,000 tokens. And for the largest open source models that I just found, it was 100,000. And this might seem like a lot, but you can really quickly get to this limit, particularly if you want to input a lot of documentation from like a manual or something like that. Or if you have an extended conversation with the LLM and any number of other things, like anything that involves numbers, because each digit is often a token. And so that you can really easily exceed this, actually, if you're using it. Hallucinations is a problem that probably a lot of people have heard about and encountered in hopefully humorous ways, but basically, it's when LLMs confidently return inaccurate information, and they're much more likely to do this with more complex tasks. Related to this is mathematical illiteracy, and LLMs are trained to predict text from prior texts that they've seen. So they don't fundamentally understand numbers. And so they might produce the right result because they've seen numbers as text in various documents. And, they surprisingly often do actually produce the right results without any sort of additional training. But the problem is especially severe for floating point numbers, where they very often are wrong. Interpretation difficulty is a big challenge. So it's difficult to understand why the output was produced, even when you're looking at the attention matrices, which are pretty complicated. And the reason this is actually a problem is because when you tune or update the models, like is often done by OpenAI, you have difficulty resolving problems without creating new problems. And finally, bias. LLMs trained to predict text from text that they've seen, largely from the internet. And there's plenty of bias in real world text documents. And so this is something that you ideally want to correct. Now, many companies will, in an attempt to correct this, will end up introducing new biases. And we've seen that recently with some pretty funny headlines. But this is definitely something that you do want to address, since it is in the raw data. Now, I'm not going to focus so much on these last two things. I'm going to focus on the first, because for analytics use cases, there kind of is a right answer that that like a human would produce that we kind of wanted to get to, and bias doesn't play as big of a role, but context limitations, hallucinations, and mathematical issues very much do. This is also generated from Firefly, and I thought it was actually, I was amazed that it got as good, although the robot is blocking the plus here. But this is actually the type of issue you could conceivably see. Well, modern LLMs have addressed this edge case very effectively. In the early days, you could actually convince an LLM that 2 + 2 did not equal 4. And it's possible you could even convince it that 2 + 2 equals fish, given that there's a lot of internet web pages that talk about how 2 + 2 equals fish, because if you flip around this 1, 2, and put them together, it looks like a fish icon. And so this is in the text data that they've probably seen. And also there's a kids cartoon in the 1990s that I watched that where one of the characters wanted to make 2 + 2 equals fish for some reason. And so that would be other source of incorrect information. So I thought this is funny. So in terms of fixing the different issues that I just highlighted, refinement methods are the kind of principal ways that you can make LLMs a lot better at, answering whatever task that you presented with. And I'll kind of address them kind of in order of what you should use if you encounter them, and explain what circumstances they should be used. But prompt engineering is the most basic refinement method, and definitely the one you should try first if you're trying to deploy an LLM. And so say you're a user or the engineer, how prompt engineering works is you actually come up in advance a set of tasks that you want the LLM to be able to do. And this might be fairly complicated, like what you see here, where there's routing to different tasks, and each task might have its own, prompt associated with it, or it could just be a single task. And then for each of these tasks, you define a prompt where you provide context, examples, instructions, how to specify the output, and various other things like that. And then once you do this, you'll ask a question that gets combined with the prompt that's passed to a pre-trained LLM that you haven't done anything to do. To update, like GPT-4, and then the answer is passed back to you. And this works pretty well for a lot of cases, and you can find videos about how to do this effectively online. But in many cases, it doesn't work. So for example, if your prompt gets really lengthy, you can run into context length limitations. And that's actually probably the most serious reason where it will fail for question and answering. And so this brings me to semantic search. So semantic search is very useful to help an LLM perform well for things that it does well with, which would be question and answering use cases, when there's potentially a lot of different context that's important to answering the question, or context can appear in a lot of different places. So basically how semantic search works is you take all the documentation that's relevant to your use case, and this could be in the form of URLs, PDFs, databases that contain language, and you split these up into little chunks that are long enough to be kind of meaningful, but still relatively short, so that you can withdraw them later and give them to an LLM without running into context length issues. And then what you do is you do an embedding. And embedding basically means you take the text and you convert it into numerical representation of the text. And this is usually actually done with a different neural network model, where it basically tries to take the text, embed it as a numerical vector, and then back transform it to reproduce the text. And then you store this in a vector store. Now, you come in later with a question that you want to ask the LLM, and you compare this question to the text in the vector store for similarity. And you can imagine like a very simple way of doing this using like a RMSE distance between your query embedded vector and then this embedded vector. But what we use is FAIS, Facebook AI Similarity Score. I included the link below. It's based off of actually quite a few papers. I didn't want to put on the screen because there's like, it looked like there's like 20 of them. And so it's a pretty complicated algorithm, but it works well. And what it does is it returns the relevant splits, or the relevant document fragments to you, which then you include in a prompt along with your question. The LLM returns an answer. Now, let's say you have a use case, though, that isn't question and answering, that you think the pre-trained LLM will not do as well with. This could include things like coding. And while many LLMs can code, they're actually generally not very good at it, because that's not really what they're primarily trained to do. And so while they can do it, they do it at a pretty basic level. Or anything that involves numerical analysis, because they are not even sort of well trained to do that. So how fine tuning works is you take a pre-trained LLM that was trained in a large unlabeled corpus. In the case of OpenAI's GPT models, it was a pretty decent chunk of the internet. And then you basically will do further training on this neural network using a small labeled corpus of kind of potential questions and correct answers. And basically then train a few additional iterations. And while I say small, this is still usually in the order of tens of thousands. So it's not like a tiny data set, it's still pretty large. And then you have a fine-tuned LLM that you can ask similar questions to, and it'll return an answer. Now, what I showed you here is not often done, and the reason this is the case is because updating all of the weights of this LLM can be extremely expensive, as there can often be billions, tens of billions or more of these weights that you have to change. When I was learning about fine-tuning for the first time, they were talking about how you should just update some of the latter layers of the neural network. And you could do something like this or have an adapter or something like that. But the problem with doing this is that the performance does decline pretty significantly. The thought was that the lower part of the neural network encodes things that are really fundamental that you don't have to relearn with the fine-tuning task. And that's definitely true to some extent, but it's not absolutely the case that omitting training these will not have a performance shortcoming. So another approach is low rank approximated update, or LoRa. And basically what you do is you take the input space, you project it down to a smaller subspace that's with predefined size R. You update the weights in this subspace and project it back to the original subspace. So what you're doing is you're updating all the ranks, but you're using a low rank approximation. So there's dimensionality, is in a reduced dimensional space, and you can't update the weights essentially with unlimited freedom. And so the advantage of this is that it's still quite fast, but it has better performance characteristics. And this is actually what we use here. And then, like any of the other methods of doing fine tuning, you would then ask a question of the LLM, it would return a result, usually with some prompt engineering as well. So this brings me to the results. And basically, we were testing this in a few different situations. One was for domain-specific question answering, which is common across all types of use cases. And so what I'm showing you here is basically how well the LLMs answer certain domain-specific questions, based upon answers that we came up with as kind of like the gold standard answer for these questions. And it was related to a marketing analytics use case. And so GPT-4 is kind of the base model, and then we have 3 other models with semantic search to see how well they perform. And these specific models, and broadly speaking, this is true across the entire presentation, were chosen because they were the top performing models at the time that we were doing this work. But there have been some new LLMs released that could be worth trying beyond these. So the first takeaway I want is, if you look at the performance of GPT-4 with and without semantic search, you can see that there's a really dramatic improvement in the results. And that would be true that's pretty much true regardless of which LLM you use. Now, the other key takeaway I want here is that if you look at this compared to another relatively large LLM, and this one actually being open source, Llama 2 70 billion produced by Facebook, you'll see that it's pretty comparable in accuracy. Ultimately, these evaluations are sort of qualitative in nature and were performed by another LLM. But ultimately, when we looked at the results ourselves, did agree with this ordering, but the difference was relatively small. And I don't think you could go wrong with really actually any of these LLMs, but in particular, Llama 2 70 billion model for domain-specific question answering. Now, if you recall to my discussion about how semantic search works, there's an embedding process. And that, as you can imagine, could have an important impact on the final results. So we tested out how different embedding methods worked. Now, we did look at kind of like the 3 best embedding methods at the time, and now there are quite a few that are ranked higher than these, but at the time on Hugging Face, these are the best 3. And we didn't see that big of a difference. Now, maybe if we picked one that ranked really badly on that list, we'd see some difference, but it appears that the results are not super sensitive to your choice of embedding method, but they are sensitive to your choice of whether to use semantic search or not. The next task is, so often when we're working with a marketing analytics use case, there's some data contained in tables, and you need to be able to access these tables. So when you ask a question, you're going to want to be able to generate a query in SQL, or maybe it's an API call to retrieve the information. And so we wanted to see how well these LLMs performed with, with SQL query generation. Now, the first thing is that fine tuning does not improve this result, because this is not fundamentally where like more context is important. But the second thing is that we tried to use fine tuning to improve the accuracy of various models. And we use like a combination of high performing open source models, as well as pre-trained models, and fine tune them in cases where we have the computational resources to do so. And then for GPT-4, it's not a public architecture, so fine tuning is impossible. So we just use few shot learning, which means that we provided some examples in the prompt to solve this problem. And so the first thing and this was done on a large open source data set called WikiSQL, and it's basically, generalizes probably to essentially any use case that involves SQL query generation. So what you can see is that GPT-4 does okay, but honestly, 64% isn't that good for SQL query generation, but that's, not bad considering it's not really trained as its primary purpose. The various open source data sets, though, do quite a bit worse than GPT-4 out of the box. But once you do fine tuning on these, you see a really dramatic improvement in accuracy from, around 27% in this case to 84%, which is much better than GPT-4. And so you can see that fine tuning is really important to getting models to perform very well for SQL query generation oriented tasks. And in fact, that's why you'll see a number of fine-tuned models that are specialized for producing code available nowadays. The other task we were looking at was tabular analysis. Now, this specific case was for a marketing analytics use case. And basically what we were trying to do was explain why a model changed. And we had a table with one row that indicated what the magnitude of the change was, and then 3 other columns that explained what caused that change. And so this is actually just a pretty basic tabular summary task that honestly, I think a 5th or a 6th grader could get 100% accurate. So keep that in mind when you see some of these performances, that this is actually a pretty easy task. So unlike in the previous slide, we show a number of different applications of GPT-4 where we present the data in different formats, because there are some questions about how well it was going to interpret tabular data that was in CSV format versus a list format, and then written in natural language, which is the text template format. And then in addition to this, we paired this with a program called LangChain Pandas, which is a specialized agent that coordinates the kind of production of Pandas code to solve these sorts of problems. And then we have a series of pre-trained and fine-tuned LLMs. We're with the only one not being fine-tuned, this Llama 2 70 billion one, because of its size and what computational resources we had access to at the time. So there's a couple of things. One is, interestingly, GPT-4 seems to understand CSV format structure. And that's actually kind of impressive to me, because it definitely was not trained to be able to do that. But I guess it saw enough tables in CSV format on the internet as part of its training routine. So that was pretty impressive. But it gets only about 70% accuracy, which isn't terrible, but is way lower than it needs to be for this task. Now, with the Pandas agent, it gets to 100% accuracy, and I'm not guaranteeing that every single tabular analysis variation would be able to achieve this accuracy, but that was extremely good. And so I think using GPT-4 with LangChain Pandas is a really good idea. The other thing is that pre-trained models out of the box were pretty horrific in terms of solving this problem, with like around a 10% accuracy, but with fine tuning, you get them up to 93% for the Falcon 40B. The 13 billion Llama model is smaller of the two, so it's a little bit lower. But one thing you'll notice is the pre-trained Llama 2 70 billion model prior to fine tuning has a 52% accuracy. So one would expect that after fine tuning, it would be somewhere above 93%, maybe all the way up to 100%. But we will have to do that studied to determine how accurate it can possibly be. But the key takeaway is that fine-tuning can really dramatically improve your performance on tabular analysis and numerical analysis tasks, which aren't something that LLMs are generally very good at doing, but you can get them to perform quite well with these. So in terms of closing thoughts, I want to conclude with like the key points from the presentation. So large LLMs paired with semantic technology work well for domain-specific question answering. In fact, as long as you ask a clear question that's contained within the reference data, I've never found them to be wrong in these cases. But of course, like handling edge cases where people ask unclear questions or a question is not contained within whatever documentation is something that we're looking into as well. Results are not very sensitive to different embedding methods, as long as you pick a reasonably accurate one, and there's a lot to choose from. Fine-tuning improves SQL query generation dramatically, even for small LLMs. What have you noticed? To the point where they really are quite good. And you probably do want to use them in lieu of GPT-4 since you can't fine-tune that method or that LLM. Fine-tuning also improves tabular analysis quite dramatically. However, specialized agents like Pandas agent may still outperform fine-tuned LLMs. And you could use Pandas agent for these sorts of tasks, and you can also develop your own specialized agents to handle certain tasks, which uses a combination of LLM and kind of built-in routines. The final comment I want to make is just about open source models versus proprietary models such as GPT-4. And basically, open source models have a number of advantages. Flexibility and control and stability of output are two pretty big ones, because I actually made like a demo dashboard like a while ago using GPT-4, and we returned to it somewhat recently just to see how it was doing, and it just had stopped working at all because they updated GPT-4 at some point. The prompt that I used, didn't work very well for whatever the reason. It just started breaking down. And this can't happen when you use your own sort of fine-tuned open source models that you have control over. Security and privacy are a major concern for many customers, and so those are benefits of open source models because it doesn't involve transferring any information outside of your company. And then cost is, of course, a consideration depending upon the engineering resources you have to develop and maintain open source models. So it very often is less expensive to use open source models. So with that, I'd like to open up for any questions, and